welcome to the lecture number 62. So, we have been discussing about the variable speed control double gimbal control movement gyros. So, in that context we have discussed about how its dynamics can be modeled. So, we have not gone into the its controls. We will look into the simplified control moment gyros and its application for the satellite attitude control. So, if you are interested in going into all the detailed controls of the double gimbal variable speed control moment gyros. So, double gimbal variable speed control moment gyros. The paper I have referred to a paper. So, you can read that paper. This paper name is nonlinear control analysis this is by Dan Stevenson and Hans Peter Shaw. So, I am not going into the nonlinear control whatsoever for this, because it is a quite detailed and we do not have that much of time to afford here, and this is was published in AS and this is paper number 'okay'. So, if required you can refer to this paper. So, it does not give you so much of details I have explained, but after a lot of effort you can work it out. Okay, so, in this context little bit whatever was remaining last time. So, we will cover that today. So, we have derived this equation, or we have written in terms of J So, this is the equation we have written, and all the quantities were converted into the body axis. So, where this G and all these quantities they are listed in body axis. Okay, so, this equation can be propagated along with the kinematics. So, x tilde you can define as say the p tilde, which is p tilde is the Rodriguez parameters, and it is a whatever the initial values are given. So, initial value it is given in this paper. Okay. So, if you are referring to this paper, so you will get those parameter values, okay, or either you can assume on your own, it is not a problem. So, p delta omega tilde psi dot theta dot and capital omega, which is the Will spin rate transpose. So, this forms the states or the state variables. Okay. So, use the quaternions as we have developed during the first 15 lectures. Use those quaternions, and from there and in your assignment the Rodriguez parameters have appeared. So, the same equation goes here in this place. So, those quaternions can be converted to the Rodriguez parameter, or directly the Euler angles you can convert to this, and thereafter you can use this equation to propagate the system states. So, so, from this place you get because this is the dynamic equation. So, once you integrate it, so you will get omega 1, omega 2, omega 3 at different time steps. This can be used to get your updated value of the p, q, updated value of the quaternions or the Rodriguez parameters. So, p 1, p 2, p 3, this can be obtained from this place using the kinematic relationship, and then you have the psi dot theta dot. So, this is for the gimbal, outer gimbal d, and this is for the inner gimbal f. So, for simplicity you can assume that you can assume that psi double dot this equal to 0 and theta double dot this equal to 0. Okay. So, the equation will get simplified, and thereafter you can integrate this equation to get the corresponding result. So, whatever is not will not appear in the or maybe some of the materials I will post as the supplementary material, which you can refer to, because it is not possible to cover everything in the class. I have tried to explain you even the mathematics in the class, which I could have put as the supplementary material, but seeing the complicacy of the system I have done that. Okay. So, the gimbal torques, they are written as u w 0 0, we can write like this in the F frame. So, your angular momentum of the body, here in this case the will. So, the will you are trying to, it is a angular momentum in the absolute reference frame, this is changing, but everything has been converted to the body frame. So, this is written in the body frame. So, we need to convert this, suppose we have this. So, we need to convert it from B to C and then C to F. Okay. So, this will get converted into, this is the angular acceleration basically, sorry, this is the rate of change of the angular momentum. So, the angular momentum change will be signified by the corresponding torque acting on the system. So, at any instant of time, whatever the torque is acting on the system. So, this is the will. So, that is acting in the F frame. Okay. As you have noticed that your frame, we have shown it horizontally in the beginning, and from here to here your wheel is there, and this is your frame F, and this will be torqued like this. Okay, so if once it is being torqued, so the corresponding changes you will get. This is for the frame F which you are torquing here in this place, but here we are dealing with the wheel. So, wheel is being torqued about this axis. Okay, so, here we have written as the in this case the F 1 cap. Okay. So, this is being torqued about this axis. Okay. So, it is referring to that. So, in the F frame this absolute angular momentum, it can be converted into the F frame. Okay. Rate of change of angular momentum, which is nothing but the torque. So, this is being converted through the appropriate transformation matrix, which we have written earlier, and once you convert it. So, this comes. So, this is along the x direction, this is the x direction or the one direction of the F frame. So, this is acting, this motor torque will be acting along this direction. So, this is how it is written. So, as a result of this, H w will change in this frame, in the F frame. Okay. Besides, you have the now this frame, because of the rotation, okay, your angular momentum of the wheel will also change, okay, because of this rotation about the F 2 axis. You are rotating the frame about the F 2 axis. So, if it rotates, so as a result, then we have to write that the wheel angular momentum, it will change because of that also. So, that has to be taken into account. So, that forms S dot wheel and of the body frame, and then this needs to be converted from the C to body, and then so, we have the outer frame here, which we have written as the D frame, and then we have chosen the inner frame, which we have written as F frame, and in this direction we have chosen F 1, F 2 and F 3, and also D 1, D 2 and D 3 has been chosen along this direction. So, D 1, D 2 and D 3. So, the rotation we are, this is F 2 and D 2, they are coinciding, but we are giving rotation about the D 2 axis, okay, which is attached to the D frame, and in the D frame your motor is fixed, which will rotate this frame, the F frame. Okay. So, therefore, we do not need to convert up to the F frame, okay, and therefore, this will be given as 0 and this is converted to the D frame. Along the same line, then you will have 0 0 u d. So, this frame also is being actuated. So, one motor is attached at this point. So, the outer frame will be rotating, okay. It will accelerate. So, this we need to convert also. So, for that, so your wheel angular momentum, this changes because of the rotation of the external motor also. So, that also we have to take into account. So, for that we write so, these are the things which are not to be accounted for, okay. And B H F dot and another one B H dot for the D frame, and this has to be converted from C to B, okay. Thereafter, we do not need to convert it. Okay. because this motor is, if we see here, we have written this as the U d. Okay. U d, this is in the C frame. So, we need only to convert till the C frame, okay. Because this torque is applied along the C 3 direction. This is the C 3 direction also we have chosen, and C 3 is a frame which is fixed in the satellite body. Okay. So, only one conversion is required and we get this equation. So, these are some of the ideas. I do not want you to go into this until unless you do a professional level work, where you have to publish research paper and other things. Okay, and if you are simulating the equation of motion, so you need to verify that your equation is working all right. So, how to verify this? So, for that you need to write the kinetic energy. So, kinetic energy will be written as so this is of the main body. Okay. Then you have to take into account the outer gimbal, and then you have to take into account the inner gimbal, which we have written by F. So, because the left hand side is a scalar quantity, it is not a vector quantity. So, directly the body component of the inertia you can choose. Okay. So, if you are choosing along the principal axis, so corresponding you will get these all quantities as a diagonal matrix I d, I f. Okay. So, and the things will get simplified, and if you are aware of the corresponding the angular velocity with respect to the inertial frame, so the work becomes easy. On the other hand, for the, if we write the same thing for the torque, okay, in the torque equation, because we have to write along a particular axis. So, in that case, if this torque will be a vector, okay. So, along the 3 axes, then you have to write, and all of them are oriented along different axes, and it is a moreover changing with time. So, for this we reduced all of them to the body axis and then work. So, here I am not giving any tag for the body axis. If I am not giving any tag, so this implies that this is in their respective body axis. Okay. So, this is for, here also I will write, this is for D frame, then F frame, and plus whatever the extra terms are remaining. So, 1 by 2 will okay. So, calculate this quantity and then take its numerical differentiation, do numerical differentiation to get T dot, okay. And also T dot will be equal to so, these are the torque applied by the corresponding motor, and the kinetic energy will change due to this. So, T dot we get from this place. If your T dot you are getting from this place and the T dot you will get from this place. So, both of them should match. Okay. So, this T dot and this T dot, they should be identical, they should be equal. Okay. Means if you do the plotting for the curve for T dot from here and T dot from this place. So, both of them should overlap, they should not do like this, they should exactly lie over each other. Okay. So, that means they have to be like this, okay. They are lying over each other exactly. I have just shown it little bit different, so that both the curves are visible. Okay. So, this is the way to verify the equation of motion that you have done correctly, and thereafter the process of the control starts, which we are not going to discuss in this class. So, under the assumption that outer gimbal and inner gimbal are massless, so therefore, their motor will also not be considered. The outer gimbal and inner gimbal are massless. So, under this assumption we have simplified the equation of motion as m external this equal to I times or the j times, where j is the angular momentum of the moment of inertia of the whole body, this h is with respect to the body axis. This we have derived earlier, body axis system, body axis system. So, so we are going to discuss this for use it for the pitch control of the satellite. So, the equation of motion we have already developed, okay. And so, if you expand this and assume this to be equal to 0, the external moment, okay. So, only the right hand side will count, and therefore, and thereafter what we have done, that we have written this quantity as h dot plus omega tilde cross h. This we have written as a u tilde or minus u tilde. Okay. Any accordingly the notation you choose. So, the accordingly the things will differ. So, your equation then looks like j omega tilde plus omega tilde cross j omega tilde, this equal to minus u tilde, and besides m external we put, let us say that we are just putting at the d tilde, which d tilde is nothing but the disturbance torque. This is the disturbance torque. Rest other disturbances are not acting on the system. Okay, so we can write it like this and plus d tilde, where d tilde is the disturbance, and this equation together. So, this is for the dynamics of the CMG with respect to the body axis, and this is the dynamics of the whole satellite. Okay, and obviously, we can write this as j 1 times omega dot minus j 2 minus j 3 okay, this part. On the right hand side, we will have the minus u tilde, and beside this, in the external torque, we will take into account your the gravity gradient torque. So, here let us make one more addition, which is g tilde, which we have written as the gravity gradient torque. Okay. So, for this reason, we will add here one more g tilde. Okay. So, this becomes g tilde equal to, so we have here d tilde and minus j 2 minus j 3 3n square So, this is the way we have written. This is for the motion along the one axis. Okay. And if we are looking for the attitude control with respect to the orbital reference frame. So, this is your E cap O 1, here in this direction E cap O 3, and inside going this E cap O 2. So, in this direction you have the n vector, n times E times O cap is the vector here. So, in this direction this becomes. So, therefore, if we want that my satellite is earth pointing, that is there is a camera here, and this camera is always pointing toward the center of the earth, So, if it is doing like this, so that means my spacecraft also will be spinning at the rate n, where n is the angular frequency of the orbital angular frequency, n is the orbital angular frequency. Okay. So, this way you can look that this omega 2, it can be written as, so the satellite is not rotating along the 1 and the 3 axis, only rotation is taking place about the 2 axis, which is opposite to the E cap O 2 axis. Okay. So, this can be written as omega 1 dot and minus this omega 2 then becomes n j 2 minus j 3 and minus this minus sign. So, that will make it plus omega 3, and this will be equal to minus u tilde plus the disturbance minus 3 n square J 2 minus J 3, and this quantity, if you remember, we have written this as theta 1. So, for a small angle approximation, if the system is disturbed from the equilibrium condition, so you can replace it later on also, it is not required at this stage, but this part is okay. If there is a perturbation in omega 2, so we have to take into account that also. Okay. So, maybe for the time being, let us write this as the omega 2 only, okay, omega 2 times omega 3, and this will put as a minus sign. So, we have developed this equation earlier, if you remember. This we have done in the gravity gradient, then the spin stabilization, and thereafter we have also this type of equation we have worked in the this gyrostate satellite. So, number of times this has been repeated. So, I hope that by now you remember all these things. Okay. So, omega 2 times omega 3, this can be written as omega 2 equal to theta 2 dot minus n and omega 3 equal to theta 3 dot plus n times theta 1, okay. And all the second order terms will be ignored. So, we look for the second order terms. So, this multiplied together forms second order term, this multiplied together forms second order term, this and this multiplied together, it does not form second order term, because this is minus n times theta dot 3. So, this can be approximately written as minus n times theta dot 3 and minus n times this term multiplied here. So, this is minus n square times theta 1. Okay. So, another term we get here minus n square times theta 1. So, the first equation we need to reduce and put it in a proper format. So, what we are doing, that we are ignoring small terms, and after ignoring it, we whatever the equation we get, that becomes our the linearized equation of motion. So, from here we get the linearized equation of motion. This is the gravity gradient term that we have brought it on the left hand side, and this is the term omega tilde, which is appearing from omega tilde cross j times omega tilde. So, small terms we have neglected here. Okay. Later on we need to insert in here in this or either need to replace the whole thing. If you want to write it directly in terms of the theta 1 theta 2, that can also be done at this stage. Okay. So, I have done it separately and so this exercise we have done in the spin stabilization part. So, I am not going to develop it completely, either you write it like this, or what we have done here on the previous page, you can utilize this. Okay. So, after using this kind of formulation, so we can reduce the whole system to j 1 times theta 1 double dot plus 4 n square j 2 minus j 3 times theta 1 So, I am here assuming that you have gone through the earlier lectures. So, look back into those lectures and so you will get these equations. And we have seen that in the spin stabilization that the motion about the two axes, it gets decoupled from the other axis. Okay. So, independent of the other axis 1 and 3 axis, we can control the two axis motion, which we call as the pitch axis motion. So, these are the linearized equation of motion, which you can check from the spin stabilization part, or either just go through the process I have told you. You write omega 2 omega 3 like this, and similarly in the same way you can write for omega 1 omega 3, you develop it, and omega 2 omega 3, omega 2 omega 3 already taken care of, omega 1 and omega 2. So, in the same way you can write, okay, where omega 1 omega 2 omega 3 I will just write now, I will write it now. Okay, so, let me finish this part. So, J 1 minus J 2 third equation, and rest your the equation of motion for this one, the gyrodynamics with respect to the body axis. So, here only the wheel motion is being considered, and wheel is rotating on its own axis, and besides because of the gimbal motion it is rotating. So, but the gimbal moment of inertia has been ignored, and therefore, the equation gets simplified, and it can be written as the linearized equation of motion for this can be written like this: h 2 dot equal to u 2 and h 3 dot plus. So, if you expand the previous equation, this equation, and linearize it, this part, okay. So, you get the this equation. So, do it as a self exercise, where we are assuming that omega 1 equal to theta 1 dot minus n times theta 3, omega 2 equal to theta 2 dot minus n, and omega 3 equal to theta 3 dot plus n times theta 1. Okay. So, using this, then you can expand and you can check all the terms. Okay. So, you will get all these equations. So, here what we are interested in doing the pitch control. Okay. So, for the pitch axis we can provide a control, because this is free from, this is independent of the other two axes, it is not coupled with the other two axes. This axis and this axis, they are coupled, but this one, the second axis, is decoupled from them. So, therefore, the control design for this can be done separately. And a typical block diagram for this, it appears like this. This is d 2, the disturbance, and here this quantity is u 2. So, look back here in this d 2 minus u 2 in this equation, d 2 minus u 2, this is going as the control input to this system. Okay. So, this is just like the torque applied to this part. Okay. So, left hand side consists of the motion variables, and right hand side purely the input to the system, out of which d 2 is the external input, and this comes from the control moment gyros, and because of this the satellite attitude will change. Here in this case, this is the pitch attitude. Okay. So, this for this, if we take the Laplace transform, so equation 2 can be taking Laplace transform of or so what we are going to do, we have to do the S domain representation for that. So, we can convert this into j 2 times, directly I am writing here j 2 times s square theta 2. Okay. If you take the Laplace transform of the equation 2, and this is 3 n square j 1 minus j 3 times theta 2. These are all in the s domain. Okay. I am writing here theta 2, but it indicates this is a function of s, which I am not writing here for clarity. So, the right hand side will be accordingly, this is u 2 s and this will be d 2 s, but again this s notation I will delete from this place. So, if you look for this, okay. So, this can be written as theta 2 equal to minus u 2 plus d 2 divided by j 2 s square plus 3 n square j 1 minus j 3. So, from here you get d 2 minus u 2, and this goes here in this place j 2 s square plus 3 n square j 1 minus j 3. And after this you get this output, we have written in the s domain. So, this is theta 2. Now, we can use a controller of the form, say we can define u tilde u 2, which will actuate the system as k 2 p plus k 2 d times s. This is written in the s domain, okay, or in the terms of in the time domain, we can write like this, okay. And thereafter we also add the integral part, which is k 2 h times s 2. This is the your momentum of the angular momentum of your gyro along the two direction, and k 2 for this the notation k 2 I we can write maybe, and h 2 dt. So, if you take a Laplace transform of this, so this will get converted to k 2 p plus k 2 d times s times theta 2, or just theta. Here in this case we are we have written in terms of theta 2. So, we will write here theta 2, and for this part accordingly we have k 2 h plus k 2 I divided by s times So, this is taken care of. As you know that the integral control is used for removal of the steady state error. So, you can use it for this system, for this control for the CMG control moment gyros momentum hold, or either you can use for the attitude control. So, both are possible in this mode. So, if we use this control, so this is the change control. Okay. So, now if you see from this place, this is theta 2 is available. So, this must be operated on by k 2 p plus k 2 d s and multiplied by this theta 2. So, that gives you the one part of the u 2. And one more part we have to add to this. this is added with this particular part. So, K 2 H plus K 2 I divided by S, and this is fed here in this place, and this operates on H 2. So, this H 2 goes here in this place, okay, and you get certain output out of this. So, this output is nothing but your U 2. So, once both of them are summed up, this is you are getting summing up. So, this is your U 2, and if you look back, U 2 equal to H 2 dot. Okay. So, this is the quantity. So, H 2 dot, this U 2 equal to H 2 dot. So, this you are integrating, and this gives you the H 2. And the U 2 which is available here, this is tapped from this place, this is brought here in this place. If there is no disturbance, then this construction of this system is very simple. However, it requires choosing these values. Okay. So, I am showing only these constants, I have not shown their sign. So, this proper sign needs to be inserted. Okay. If there is disturbance, so those disturbances need to be rejected. So, for that a disturbance rejection filter is added here. So, this part we are not going to discuss as a professional work, or if you are doing some particular course on the control of the satellite. Here we have done the dynamics part extensively, only if the controls is involved. So, on the MATLAB you can do all the control design for this. Okay, so, remember that here theta 2 we are showing only. So, theta 2 is the angle measured from the theta 2 is measured from the two body axis. If we take the first rotation about the, because your system, this spacecraft is rotating. So, the first rotation you will give about the 2 axis. Okay. So, theta 2 is measured from the 2 axis, and thereafter you will give the 3 and 1. As we have done in the case of the spin stabilization. Okay. So, theta 2 is the reference value of theta 2, this equal to 0, theta 2 reference. So, and therefore, if you see here in this place, we have not kept any the reference value, because theta 2, otherwise you can formulate the block like this. You can put here theta 2 reference. Okay. If you need some other value, and then this goes as plus, and then from here you can take this as minus, and this comes as theta 2, and formulate this control block in terms of that. Okay. So, the same thing can be represented here in this format. Okay. So, if you have to do the disturbance rejection, so this theta 2 has to be tapped, and this is a tap whose position you can change. So, this position here it goes for the control moment 0 momentum hold. Okay. I can take it using from here it goes. Okay. So, this is the point. So, this needs to be flipped into this position. So, this is for CMG momentum hold. So, this structure is simple, but you need to choose these values carefully, and this may require a lot of effort, and there are the sophisticated version of this also. So, you can look into the book by Bongvi or by the Marshall J. Sidhi. Marshall J. Sidhi. These books names already I have given you. One by Bongvi, another book is by Marshall J. Sidhi. They are two different books. So, many controller structure you will get there in that place, and the satellite attitude control for the linearized satellite dynamics has been considered there, not for the nonlinear control. Okay. So, if you have to do the nonlinear control, so but I will be doing one nonlinear control part. Nonlinear control means you are proving the stability of the designing control for the nonlinear system. So, your control input may be in the linear format, means you may be putting the control in this format, let us say k p times theta and minus k d times theta dot. So, this is just the proportional and the derivative control, but if you consider a system without linearization, so that becomes your nonlinear system, and then proving the control for that, that may be tough. Okay. But I will do that one case for the magnetic attitude control, which needs little extensive calculation also, but I will do that. This part you can look into the book by Bongvi and Marshall J. Sidhi if you are interested in further simulating the satellite motion. You want to launch your own satellite for your institute. So, go through this part and you can do the local control, but if you have to do the control in a wider sense, means for a larger value of theta and other things, other variables, then you need to use the Lyapunov stability analysis and do the control design accordingly. So, here this equation that we are taking up here, this part, one part I will show it to you on the next page. Say H 1 dot, H 2 dot and H 3 dot. This is for the CMG motion, and obviously, this is a simplified version, because we have neglected the internal and the external gimbal mass. If we do not neglect it, then for the double gimbal variable speed control moment gyros, whatever the procedure we have followed, that procedure needs to be followed, and thereafter the control has to be designed. So, U 1, U 2 and U 3. So, just let us look into the H 1 dot. So, this becomes omega 2 times H 3 minus omega 3 times H 2, this equal to U 1. I will just do for one, rest others you can do it yourself. Omega 2 is obviously this is theta 2 minus n, and this is H 3, and omega 3 equal to theta 3 dot minus plus n times theta 1 times H 2, this equal to U 1. So, here if you look, these quantities are small. Okay. Initially, we do not have what are the conditions set that H 1 equal to 0, and similarly, we have we can put H 2 equal to 0. No, this part, this is part for the rotor dynamics. We will sorry, H 1, H 2. These are. Let me explain you what we are doing. H 3 minus n times H 3 minus theta 3 dot times H 2 minus n times theta 1 S 2 times u 1. So, this quantity is and this quantity they are small. Similarly, here theta 2 dot S 3, these two quantities are small. So, they will be almost negligible. Here also this quantity, this will be almost negligible. So, this part will get 0 and we get here H 1 dot minus n times S 3 equal to U 1. So, here initially your H 1 may be 0, H 2 may be 0, H 3 may be 0, this is the initially it may be. Okay. But as you actuate the gimbal, okay, so no longer your H 1, H 2, H 3 will be 0, okay, but the initial part it may be 0. In a gyro state, say in the gyro state if this there is a rotor and this is the main satellite. So, this rotor may be rotating, okay. Let us say it is rotating and it is J is its angular momentum of this one. So, in that case this is fixed along certain axis, okay. And for that already for the gyro state we have written the equation. So, you can utilize this equation and reduce it. So, for that part your objective will be to keep the satellite oriented along a particular direction, okay. So, there it may be required that this part is de-spun, and therefore, this is not rotating at all. So, accordingly we have to choose their angular momentum. So, let us say this is 1 2. So, H 1 may be set to 0, H 2 it is set to 0. Okay. Along the H 3 direction its rotation is there. So, this will appear if this is the H 3 direction. So, for the satellite this will add there, but here in this case as you rotate the gimbal, okay, so the H 1, H 2, H 3 which are initially 0 they will not be 0, okay. But these together they constitute small quantities and therefore, they are getting dropped and you are getting this simple linearized equation. If you are considering the nonlinear system, so you have to take this equation as a whole, okay, not a linearized one. This is the linearized part you are writing omega 2 equal to theta 2 dot minus n, this is a linearized part for omega 2. Okay. Similarly, for omega 3 this is the linearized one, okay. You have replaced this omega 3 by this linearized value. So, you can follow this notation and then where the product with theta or theta like the theta 1 H 1 this term occurs or either terms like theta 2 dot H 3 which is present here if it occurs. So, this kind of terms will be 0, okay, almost 0. So, they are getting dropped out. So, if you do this, so you get the sets of equation we have shown here in this place. So, obviously, this is based on using these values. In the case theta 2 is large, then we cannot quantities related to theta 2. So, for that you have to write equation separately. So, for this part you can refer to Bongui. Okay, these are mechanical exercises which I should not do here. Okay. This can be done once you have learned the basics. So, you can do it any time. Okay. Okay, these all little bit of mathematics required to work it out. So, we stop here and we will continue in the next lecture. Thank you very much.